the intention of what I wanted to talk about today was very much a bit of an overview of satellite technology. We've done some work with the EAGE in the past through the work that I do with the Geological Remote Sensing Group, which I'll talk a little bit about as we go through. And it's a nice, there's a lot of overlap, I think, between the two groups, but also a lot of difference in levels of knowledge. So what I wanted to do here was provide a bit of background, provide some examples, and just start to maybe spark some interesting ideas as to how Earth observation data, which is the EO in GEO, is able to help for a range of different applications. So I'm using this as an opportunity not just to present the work that I do, but also of some of our partners through GRSG. So you'll see some other logos on slides that have been kind of kindly provided some case examples to us that I can talk through and explain, just to show you the diversity of what's possible. So I guess to start with, when we think about Earth observation, or satellite imagery, many of us may think of Google Earth. It's probably the most used visual tool, easy access GIS tool that all of us have on our computers. We use it daily here because it's such a fantastic resource. And it's a great way to start a talk, I think, on remote sensing, because it's exactly what it's showing. The data that's included in here is largely collected from satellite. It's also collected from aerial images, and it's compiled into this wonderful skin around the Earth that we can zoom around and we can zoom in at different levels of detail. But there's not a lot we can do with this data. It's great as a view, as a visual view of a particular area of interest, but we can't drill down into that. We can't analyze it. We can't classify that data. But we have a bit of a conundrum because there's so much data, and it's sometimes a little bit hard to navigate what that looks like. So this is just a graphic my company makes. So I'll tell you a little bit about what KSAT does. So KSAT is a ground station as well as a value-added service provider. So that means two things. We have antennas across the world which are interacting directly with satellites and pulling all those down through our antenna system and then providing those to the satellite operators. So we work closely with all of the satellite operators, or pretty much all of them, in helping them deliver the data to the users. But we also use some of that data ourselves for the products and services that we make. And a lot of that data is used in oil and gas. A little bit in mining, but not so much, I would say, at KSAT. That's not a key area for us. But oil and gas, situational awareness, lots of logistics. We also do a little bit of defence and environment mapping as well. And there's so many different applications for the data that we're going to look at some examples of today. And I think that's where it's quite interesting to see the range that's out there. And I could probably talk for hours on everything that is available and what that all means. But I'm very happy to answer questions on that when we get to that stage. But this example is one that our operations team had made to showcase how satellites orbit around the world. So every time you see the same colour, so the blue, for example, it's one satellite and it's going around the globe north to south. Some satellites have a slightly modified orbit, but most of them are in a polar orbiting, travelling north to south, and that takes about 90 minutes to do. And depending on how wide a view they have of the Earth will depend on how quickly they can get back to that same place. And that could be very important for different applications. So this example is just showing some radar satellites, and I'll show you some examples of what I mean by that for those who might not be familiar. But what we see is that this is only showcasing 4 or 5 different satellites, but we're getting quite a lot of overlap. We're getting a lot of different data, a lot of almost redundancy to a point. But what that means is we have options. There are now more options than there was when, significantly more options than there was when I came into remote sensing nearly 15 years ago. And there's so much more we can now do with the data. So I hope this presentation goes some way to show what that means. So often the first challenge is finding the right imagery, and that's not necessarily knowing the right satellite to choose. We're past those days of selecting, requesting a particular satellite, because there are too many to remember, aside from anything else. And actually, what's important from a user perspective is what you can do with it. Can you answer your question with the data that is available? And I think even more so now than ever, there are so many more questions that satellite imagery can help to answer, and they are just one tool in the myriad of tools that we probably all use day to day, or our companies use to help improve decision making and reduce risk in the activities that we have. So there are several considerations that we might have in relation to finding imagery. So for example, spatial resolution. So this means the level of detail, how clear is the image? So from left to right, you see an arrow. So anything with an arrow, the arrow head means it's a higher cost in this case. So spatial resolution is high. But also cost is high in this case. So the more detail, you pay a little bit more for that. On the flip side of that, if you want to cover a larger area, often the cost of that is very low, if not free. So there is a balance, there's a trade-off between the different requirements that you have and how that fits with what's available from the world of satellites. So to show you a little bit more about what I mean by spatial resolution, so the detail that you see in an image. So this is an example of sorry, my animation has gone a bit awry, but so this is a 30-meter pixel example. So each of these little squares you see on the screen are 30 by 30 meters. If we step that up and we go to 15 meters, then we're starting to see a little bit more detail. We start to maybe be able to tell what we're looking at here. We're quite zoomed in. And then we go to 10 meters, we can see much more detail. Sorry, 5 meters that was. And then this is 50 centimeters. And the highest we can go with satellite right now is 30 centimeters. So we get a considerable amount of detail. We're quite zoomed in. This is a very large mine area, but we've had this enormous range of satellite data that covers from, say, 30 centimeters up to 30 meters or higher, depending on, and the usability of that data will very much depend on what you want to do with it. So the other step to considering different types of data, or the application of satellite data, is the use of color. So, and I'll show you what I mean here. If we just blank out the rest of this graph for 1 second, we see that actually we only see with our eyes in the red, green and blue. So this is what we see. This is why we see vegetation. This green line is vegetation. This is why we see vegetation as green, because it reflects the light it reflects is in the green part of the spectrum. But actually everything on Earth has a unique signature. Whether we can identify it from a satellite is a different matter, but everything has a signature based on the reflectance patterns of the light. And as we move further into the emissivity, the thermal range of the spectrum, then there are some other characteristics there that can be explored and may be very useful for geology. And then if we look at the whole of the spectrum, suddenly we see there's this vast amount of information that is beyond what we see visually. We would never see these features unless there is a capabilities with the satellites that covers some of these areas that we don't see naturally. So we can use that information by these we call them spectral ranges. We can use these unique bands of information at these different spectral ranges along this area that we see outside of our visual view, and use that to help map different materials. In a geological sense, we can use it for mapping lithology, and I'll show a little example of that. And we can also use it for mapping minerals. We can use it for looking at anomalies related to hydrocarbons. The possibilities are endless in terms of it more comes down to the technology capability to be able to meet the need that you have. So to kind of show this a little bit more visually before we dig in a little bit more to some examples as we go through. Spectral resolution is essentially color. So we just talked about color, but what we would term it in our world is spectral resolution. So separate to spatial, which is the detail that you see in an image, spectral is related to the color information of the image. So the image you see on the screen, we're in Flinders Range in Australia here. This is a nice Landsat image, which may be a satellite sensor that many of you have used before. And this is what we would call a natural color image. So it's as close to a true color, the type of information you'd see in Google Earth. So this is what we would see more naturally in this area if we were looking at it from above and having the same perspective. But what we can do by using these spectral information that's outside of our visual range is suddenly we start to highlight features that we didn't know was there. You know, this area in natural color can look a little bit bland. It doesn't show a lot of contrast. It doesn't show a lot of variation. And just by moving to optimizing, shifting, we're only shifting by one step in this case, in this example. And what I've done here is move to the near infrared. So, and the value of that is that we actually see vegetation has an even bigger reflectance peak in the near infrared, but we just don't see it. So we see vegetation as green, but actually it has this extremely strong peak in the near infrared. But what that allows us to do is actually separate features that aren't vegetation and see different characteristics. So vegetation is red in this case, but we start to see some different layers in the lithology here that are not perhaps visible just on the natural color alone. And we can take that a step further by looking more into the spectral range as we move where a lot of the spectral features are for geology, and we start to see even more information. So this is quite a nice visual way to show what's possible, and then we can dig into that deeper and extract features of interest. And we'll show some examples of what that can look like from a mining example. Oh, we'll get to that in a minute. So the other thing to consider is what type of data. So as Artem said in the introduction, there's different types of EO data, satellite data. It can be optical, so an image similar to what you see in Google Earth, exactly the same as what you're seeing on the screen here, which can only image in daytime because they are essentially a camera and they rely on reflectance so they need the sun to provide the light so that they can capture the image. And the other option is radar. So radar is an active sensor, meaning it sends and receives its own signal. And what the image that's compiled from that response is based on the interaction of that signal with the ground. What that means is that we don't have to worry about the weather. We can image day and night. We can image even increasingly now at different times of day. And we can start to see more information, particularly in areas like we see here in PNG, which are very cloudy normally. And then suddenly we can have a radar image of exactly the same area and we can see different information. Now radar is very different to optical, has very different properties, and I won't go into the detail of what that is specifically here, although I'll show an example later of the value of integrating the different data sets together. So it may not always be a choice between the two. It may be that combining that data together has a lot of value. And that could be because of the unique properties of the radar. Radar is essentially measuring the texture of the ground. how rough or smooth that is has an impact on the response that goes back to the satellite. Whereas optical is only really seeing what's on the surface and how we would see it, but just in a range of different spectral information bands. So there's a lot of difference between the tools that are available, and there's quite a wealth of different satellites that cover these both optical and SAR that can be used for these different applications. So then to move, as a kind of slight segue, but as we move into applications, we have optical and radar data, but we also often use terrain data, and this is terrain data derived from satellites as well. So an example here is the SRTM, the Shuttle Radar Topography Mission, which is an elevation product that I'm sure many of you have probably heard of. It's from the USGS. And what is also possible from a lot of the satellite systems that are orbiting is that you can also derive higher resolution focused on particular areas of interest, different levels of detail that can be very complementary to, say, a site survey or logistics or accessibility, particularly in remote areas, or, for example, at this time where actually traveling to places can be more challenging, and being able to get an up-to-date view of your area of interest may be of interest, if you see what I mean. So this example just moves from the SRTM, so the 30-meter gridded product, to a 1-meter gridded elevation product. And actually we can get elevation models down to 30 centimeters or 50 centimeters with some advanced techniques. So it becomes much more accessible. This data can be processed quite quickly. The only, I guess, caveat to that is it's often not collected all the time. So you may need to have a special request to collect imagery, but there are a range of different sources. It doesn't have to be 1 meter or 30 meter. There are a number of options in between that, some of which are off the shelf and ready to use, and for a small cost can be extremely valuable to support different operations. So to keep on the theme of terrain mapping and to move to our friends at PCI Geomatics, who are a Canadian software company, they provided these next two slides are really nice examples of different things you can do with terrain data. It's not just the topographic view, but it's also slope information, aspect, and shaded relief. And what that's really valuable for from a geological point of view is that you can change the view, change how the sun is looking at the terrain, the virtual sun is looking at the terrain when you make your shaded product, and use that to your advantage to help highlight features, faults and lineaments and fractures that you perhaps wouldn't see naturally on a single view without taking into account the different highlighting with the sun at different angles. If you're only looking at one image at one time of day, it can be quite challenging to see all of the different detail. So to go into a bit more of an example, and this is from our friends at KSAT, this is a Landsat imagery, and I won't speak too much about the particular images here, because actually the image is almost irrelevant, because a lot of the examples here can use a myriad of different types of data, and it can be done at a range of different scales. But Landsat imagery is a good one to mention because the data is free. There is a vast archive back to 1972. And it's still going. It still continues. They're planning to launch a Landsat 9. So there have been 7 before. One unfortunately didn't make it to orbit. So even though we are on Landsat 8, one of them did fail before that. So there have been 7 historically. Excuse me. And then there will be another following in the next few years. So Landsat data, just to give a base map image, in this case it's a slightly optimized color. It's not just a natural color, it just provides a little bit more of a visual interpretation base. Adding that with the shaded relief from the SRTM, so a low resolution elevation product, but ideal for looking at regional mapping. And then actually in this area, they also had LiDAR, not from space, I will add. This is LiDAR collected over a large area of PNG that it has become a more publicly accessible data set. And they also use that because, of course, there's a significant amount of detail that comes into this. You could use similar with a high resolution spatial satellite data set as well. But of course, it becomes a challenge in some areas because of cloud. So what he's done here is then combining all of this data together and then extracted the larger fault features, some of the lineaments, and then we can see a lot of these different clusters of information around that he's interpreted from the terrain information in combination with the Landsat. And then mapping that as a density map, looking at the trends within the faults and fractures and how that correlates with the overall trend of what is an anticlinal feature in this area and how that's kind of affected the dominance and the, I guess, density of some fractures that's quite associated with that trend in the area. And then we can take that a step further and not just look at faults and fractures, which has been done traditionally with satellite data for a long time over regional scales and definitely over more focused scales as a reconnaissance or screening tool to help exploration activities, but also lithological mapping in the same way as we talked about spectral and colour and different information we can find by looking outside of what we can see visually. We can use this to our advantage from a geological point of view and start to highlight features of interest. So this is another publicly available product. It's actually another Landsat based product, and using that again with a combination of an elevation model, in this case combining it with a data set called ASTA, which has a wider spectral range, which has a lot more information, very good for geological applications, and using some different techniques to enhance the features that can then be used in combination with some radar data. This looks a little bit different to the image we saw previously, and that's because it's a combination of different channels of a radar. I won't go into too much detail of it gets a bit complex, but the way the radar sends and receives a signal can be varied. And what that allows us to do is look at subtle differences in surface texture that may be reactive to these slight modifications. And this is the result. You get a combination map of these different channels that can greatly aid in interpretation and provides different type of information than we get from the optical data alone. So then interpreting faults and structures again, and then using the information that we see across the different images to then extract the information related to the lithology as well, and overlaying that together and providing often a more detailed map than may be available in some areas, particularly remote areas. Satellite imagery is a fantastic tool to help improve the geological information, particularly as part of a desktop study associated with screening an area. And also, as I mentioned, we can use the same type of information for mapping minerals, but it could also be for mapping lithologies just in a slightly different way. So mineral mapping has been done for many years using satellite data, and the application of that has changed over time as the capabilities of satellites have also changed. So there is a bit of a workhorse in the industry has been this ASTA data. And so our friends at ITC, which is a research institute in the Netherlands, provided these nice examples from the south of Spain, where they were looking at mineral alterations by using satellites. So these are just surface expressions. There is no ground penetration, but it's because we can look at the alteration on the rocks based on this spectral response of features that we cannot see with our eyes, but we can see by virtue of satellites. We can start to map different features. Now this looks a little bit of a cluttered map. It's a little bit noisy. We're quite zoomed in, and we're seeing some artifact features, but the red here is showing clay concentration, and we are seeing something, but we maybe need a little bit more information to help us define the detail around that. Please ignore the red along the coast. This is an anomaly, which is often well known in the processing of this data. But if we move to a slightly higher resolution, a very much higher resolution data set, that at the time of this example being made was at a lower resolution than is actually available now. There is only one other satellite at the moment that has the same or equivalent spectral information to the one we just looked at, and that's called Worldview 3, which is a commercial satellite. Aster is free, it's publicly available. Worldview 3 will typically have to be tasked over many areas to collect data that might be of interest. So we're looking at exactly the same area. Already visually we can see more. And by applying the exact same algorithm, we can see so much more features. So we can see the density of the clays. We're actually seeing them in the same areas, which is great. That's what we would expect to see, but we're seeing it at much more detail. Now, both of these different resolutions, spatial resolutions, have value. It really depends what you're trying to do, whether you're looking at a broader scale or whether you're trying to narrow in or more detail, or whether you want to use a combination of the two to help better focus a study by using a regional study first. And then moving on to radar imagery and looking at oil slicks. So this is something my company does quite a lot of, and it's detecting oil on the water, so not on land in this case. And radar data is extremely good for this because, as I mentioned, this response that it sends and receives over water, there is often a very clear separation between what's oil and what's water, just because of how that signal reacts with the signal of the radar. So this is the type of thing that we do routinely. We do a lot of emergency oil spill detection reports and support a range of different applications, from oil and gas companies to environment regulators. And this is just a nice example. It's another radar image. This is the Gulf of Mexico, and we see these huge areas of slits. These may not all be pollution. They may not all be very big. Some of them may be natural seeps as well, and they can be confused with other features. But it's a great tool to use for this application, and with experienced analysts, it's a fantastic resource to monitor and build up knowledge on an area, particularly in the maritime domain. And this is just a nice example. This was from an incident that happened last year, and actually getting some high resolution optical data over the oil spill. You can see the facility towards the bottom right of the screen, and then the oil booms that were put out to try and stop the large oil leak that happened from the facility. And optical data isn't often used in this context because it has different properties. It's often quite difficult to discern oil from other materials in the water, but it does have a lot of uses at times, and it certainly can be used as a tool in an emergency situation to help provide more context and a situational awareness to support the cleanup efforts. And that can also link, and just very briefly touching on other applications, and it's not geological as such, but using the same type of technology to link that with vessels, support vessel transits, provide information on potential polluters by integrating that with information from AIS systems, and then building a picture around the transportation networks and potential areas and access is another thing that we do quite a lot of at KSAT as well. And then the last couple of examples I have here, and this is I must thank my friends at CGG MPA for this. This is some work that they've been doing for many years, but I love this particular example. This is an actual pub. It does exist, and it's just a really nice example of subsidence in reality. But we can actually monitor this from satellite. So it's a geological application, it's also an engineering application, and we can monitor how an area is changing, either instantly after an event, for example an earthquake, or how it's changing over time related to construction, for example. So the example that we have here is related to Crossrail. And you'll see an image at the top and the bottom. So we have the kind of baseline image for comparison. So the red areas are areas that are have moved down. But it's just to bear in mind that there are a lot of other things that need to be taken into context in interpreting results like this. And I'm only really going to concentrate on the relation related to construction. We're certainly not saying that these very large areas are subsiding significant amounts, so I don't want that to be taken out of context. But just to give you an indication that actually satellite technology we're only seeing the surface, but by using these particular techniques, we can start to infer how the geology or the ground is moving underneath the surface based on different techniques that we can apply to the data. And this is a technique called interferometry, and I can answer some questions about this if anyone has any questions when we get to that point. But what this is showing is that green areas are largely stable. Blue is areas of uplift. I'm just trying to see if I can find any, but we do have some areas which are showing some subsidence, and that could be related to shrink and swell with the clays. It could be related to the weather at the time. There can be a number of reasons, and these movements will be very small. These are millimetric changes. And the image at the bottom shows a lot more red, and that's because of the construction that's happening under the surface, that's having an impact on a very minor impact on the features above, but we can measure that really minor impact by using radar technology through interferometry. And if we click on, we can see some of the stations are actually associated with some of these red features, which is related to where they've done extra tunneling, where they've had to do extra excavation, and then we can start to build a picture of how those features are moving. What does this actually look like? This is in millimeters here. And so these are the features around the construction phase, and we can see that there's a period of subsidence associated with that, but also there is a period of settlement. So this is not saying this is going to subside for a long time, but it's a way for the area of movement to be monitored remotely and to understand that motion. The engineers have factored in the fact that there will be motion, there will be some subsidence associated with this, and they can use this technology along with their other survey and levelling materials to ensure that it's not going outside of that range. And then Lambeth and near Waterloo is provided as a reference point, since it is not moving during this time. And just before I skip to the last, I mean, there are so many applications. I could have spent a very long time going through all of those and explaining them in more detail, but hopefully that gives a little bit of a flavour as to the range of different applications that are there, perhaps some of the different data types or considerations that can be thought about when deciding whether or not to embark on using satellite imagery. And what I will say is that satellite imagery, the access to it has become increasingly easier. Perhaps from a user perspective, it can still seem quite daunting, but pricing has become more accessible. The range of different solutions certainly makes that a lot easier. And then suddenly it becomes an accessible tool for everyone to access, and it doesn't have to just be data. I mean, what we see a huge trend of over the last few years is information. It's slides like you're seeing on the screen now, where the important information is not the radar imagery that made the product, it's the information the product is providing. So it really does depend on what you want to do with the data and how different types of data may add value. And I just, as a very last slide, but a little bit of a push related to the work we do at GRSG. So GRSG is the Geological Remote Sensing Group. We are our parents are, sorry, I should say, the Geological Society and the Remote Sensing and Photogrammetry Society. So we're a group of essentially geology, and I would say geographer in my case, enthusiasts who work within the industry of geological remote sensing in some form. And we are a committee made up of engineers, of commercial business, of satellite operators, of service providers and students, and we bring together every year an international event, which we were really looking forward to having in person, but unfortunately that's not to be. So we do have an event coming up in December. It will be across 3 days, but within short sessions across those days. We do still have the call for papers open. We would love to hear from you. It's going to be, if you're new to the GRSG, it's going to be something that I think will spark a lot of interest and we hope discussion. And if you're already an existing member of GRSG, it will be very different to what you've seen before, but we certainly hope will be a good way to round off this rather strange year. So with that, I will say thank you, and I will open up the floor to questions.